Hello everyone, I'm Yao Li from Chang'an University. In this lecture, we are going to learn some basic knowledge about Coulomb's earth pressure theory. Rankine's theory assumes zero wall and soil interface friction. In practice, there is friction between wall and soil. Wall and soil interface friction affects the earth pressure on the wall as shown in the figure. Coulomb proposed that a condition of limit equilibrium exists in a soil wedge between a retaining wall and a trail slip plane. The force between the wedge and the wall is determined by considering the equilibrium of forces acting on the wedge. Among the trail slip planes, the critical slip plane is the one which gives the maximum lateral pressure on the wall. Coulomb's theory assumes that the backfill is dry, homogeneous, and cohesionless soil with internal friction of phi prime. The backfill is sloping at an angle alpha to the horizontal. Wall friction delta prime is present. Wall face incline at the angle theta to the vertical. To use the limit equilibrium method, first we need to select a plausible failure mechanism. Then determine forces acting on the failure surface, and use equilibrium equations to determine the maximum thrust. This figure shows the calculation model for Coulomb's active earth pressure. AB is a backface of a retaining wall supporting a granular soil, the surface of which is constantly sloping at an angle alpha with the horizontal. BC is a triaxial failure surface. In the stability consideration of the probable failure wedge ABC, the following forces are involved. W is the effective weight of the soil wedge. F is a resultant of the shear and normal forces on the surface of failure BC. This is inclined at an angle phi prime to normal drawn to the plane BC. PA is active force per unit length of the wall. The direction of the PA is inclined at angle delta prime to the normal drawn to the face of the wall that supports the soil. Delta prime is angle friction between the soil and the wall. The fourth triangle for the wedge is shown in the right figure. From the law of sines, we can get the first and second equation. The preceding equation can be written in the form of equation 3, where gamma is the unit weight of the backfill. All variables except beta are constant. To determine the critical value of beta for maximum PA, we can use equation 4 when the relationship of the beta is substituted into equation 3. We can obtain Coulomb's active earth force as equation 5, where Ka is Coulomb's active earth pressure coefficient, given by equation 6. Physical meaning of each symbol used in previous equations are listed for better understanding. Now let's consider a special case where the wall is vertical, there is no friction between the wall and the soil, and the surface of the back wall is horizontal. Coulomb's active earth pressure coefficient becomes equal to Rankine's earth pressure coefficient. After we have got the Coulomb's active earth force, we can use equation 1 to calculate Coulomb's active earth pressure. According to the fourth triangle, we can also determine the horizontal and vertical active earth force as shown in equation 2 and 3. The left figure shows a retaining wall with a sloping, cohesionless backfill similar to that considered in active earth pressure condition. The fourth polygon for equilibrium of the wedge ABC for the positive state is shown in the right figure. PP is the notation for the positive force. Other notations used are the same as those for the active cases. In a procedure similar to the one we followed in the active case, we can get the positive earth force, Coulomb's positive earth pressure coefficient, and positive earth pressure. Now, let's consider a special case where the wall is vertical, there is no friction between the wall and the soil and the surface of the backfill is horizontal. Coulomb's passive earth pressure coefficient becomes equal to Rankine's earth pressure coefficient. After we have got Coulomb's passive earth force, we can use equation 1 to obtain Coulomb's active earth pressure according to the force triangle. We can also determine the horizontal and the vertical active earth force as shown in equation 2 and 3. For vertical force, where theta equals 0, Coulomb's active and passive earth force in horizontal and vertical directions can be calculated using given equations. Wall friction causes the slip plane in both the active and passive states to be curved. The curvature in the active case is smaller than that in passive case, as shown in dotted right lines, but in the calculation, the slip surface is simplified to a planar slip surface, as shown in the right lines. Since the Ka and Kp are based on planar slip surface, so the Ka and Kp are not accurate. For the active state, the error is small and can be neglected. For the passive state, Kp is overestimated. The error is small if delta prime is greater than 0 and smaller than 1/3 of the phi prime. But in practice, delta prime is generally greater than 1/3 of the phi prime. This error is somewhat unsafe for the design purposes, so we need to consider the effect. Generally, the earth forces are inclined at delta prime to the normal on the sloping wall face. The Coulomb theory uses the limited equilibrium method to obtain the lateral active and passive forces. In the limited equilibrium method, a collapse mechanics is selected to represent the failure of the material. Each block of the mechanics is assumed to be a rigid, perfectly plastic material. In the calculation, the slip surface is simplified to a planar slip surface. Here are all the contents in this lecture. Thanks for your listening and see you next time.